come up with a Cartesian equation, it's called. So we're going to put it in like what, quote unquote, a normal equation, an equation with x and y in it. Guys, can we stop talking, please? Okay, so the first thing you do is really it's just generating. So like x, it represents square root t, right? So all you do is you take the square root of each number, right? Sometimes like the table is given for values, sometimes you have to come up with it. So just be strategic with it. Like if you're doing square roots, like don't pick 2 because the square root of 2 is like gross. Pick like nicer numbers, make your life easier. And then so those are all your x's, and then your y's are determined by the t plus 1. So you're just plugging in 0 in for t, so and 1 for t. 4 for t, 9 for t. And then what you do is we're going from 0 to 9. So you have to plot the first point first, which feels obvious, but you never know. So you have to start here. So you graph 0, 1, and you put like a dot, obviously. And then as you graph the points, you put like an arrow on the curve. So you go, the next one's 1, 2, and then 2, 5. Wait. Oh, the thing's like above it. Okay. 2, 5, and then 3, 10, right? And then when you connect them, make sure you have like the arrows as you go. So that would be what it looks like. You can kind of have an idea of what like graph it kind of looks like, like it looks kind of parabolic, so you can have that kind of in the back of your mind. But if you have to find a Cartesian or rectangular, they call it rectangular because it's like you're going left and right, so they call it rectangular for like a normal XY coordinate, or Cartesian is the name of the plane for the fancy way, but essentially it's just like hardcore system of equations. Whoops. So it's essentially you have your 2 equations, right? And you just need to solve it using basically substitution is usually what I use all the time. So I usually solve for t in one of them. So like for this one, I'm going to solve for t, get x squared equals t. And then I'm going to plug in the x squared in for the t over here. So I get y equals x squared plus 1. Okay, so that's what's called the rectangular or Cartesian equation. And you're like, oh my gosh, that looks like a parabola just up 1. This is so shocking. It's not shocking. And then as far as the bounds go, I mean, you're going from t from 0 to 9. We'll look at your domain on your x, right? So your domain is from 0 to 3. So like to represent that I'm not just doing the full parabola, I'm just working with between 0 and 3. So I guess I should have circled all that, but. So like t has your parameter, so then your Cartesian equation should have a parameter. So, okay, so there's one. That's like an easy one to start. Not too hard to solve for. And then for this one, it's the same thing. So you're just doing like hardcore plugging in to start. So you get t squared minus 2. You're going to plug in. And then t over 2, and you're just going to throw in the t's for all of them. So you guys know how to plug things in, so I don't think that's an issue, but you're just plugging in 3 squared minus 2, 2 squared minus 2, yada yada. And then for the y's, you're going -2 divided by 2, -1 divided by 2, 0 divided by 2. That's all. And then you're going to go ahead and graph it. So, again, your t starting at -2, so don't be weird and start midway through your chart. Like start at the beginning. So this is going to be 2, -1, -1, -1/2. So again, make sure you're kind of paying attention to what direction you're going. And then -2, 0. And then -1/2. And then wait, where am I? Oh yeah, 2, 1. Jesus. 2, 1. And then 7 3/2. Okay. So it's like a little sideways action, right? Okay. So you guys have learned like more graphs than like a normal math student. So when you're doing your Cartesian equation or your rectangular equation, like the one we just did, hopefully you have some insight on like how this equation should be set up. Okay, so I'm going to do write them both down. Okay. And then I got y equals t/2. And if you did a Cartesian equation, right, this is like a sideways parabola kind of, you know. So like if I was doing like the normal up and down, it would be y equals, like I'm used to this kind of transformation. It's up 1, whatever. But for something that's like a sideways parabola, really a better way to write that in standard form is solving for x. Okay, so working with the inverse function of it. Because if you solve for y, maybe just jogging your memory, if you solve for y, you would have to deal with the plus or minus part of it. So you'd have to deal with the positive root and the negative root, which is pretty difficult to like talk about with a domain when you're talking about this. So like sideways parabolas like that is usually a hint that maybe you should solve for t in the y equation. So like I should solve for t for this guy. And then when I plug it in, so I'm going to plug in the t here, I get x equals, I'm going to throw this in, -2, so this isn't too horrible, and simplify it out. Okay. So in this form, I don't have to deal with the plus or minus piece. Because like if I did y equals, I have to deal with the positive root part of the graph and the negative root part of the graph. So if you've got like that sideways thing again, it's a little easier to work with an x equals equation. Then if you're solving for x, right, your independent variable is now y. So really, you know how before we had x's, because x was the independent variable that I'm plugging in, and we wrote the domain as 0 to 3. This one, y is in the equation. So you should talk about like, okay, here's my parameter on t. I don't want the whole sideways parabola. I only want between when y is between -1 and 3/2. And where do I get that? Well, oops, I should put that in blue. Is just look at the table, right? If you look at the table, the smallest y is -1, the biggest y is 3/2. So if you are going to put the equation in terms of x, which is fine, it's still Cartesian. If your y is like in the equation, it means it's an independent variable. That's why you're going to talk about that as like your domain in a way. That makes sense. This is my favorite one. I love this one. So the Cartesian equation is fun to do. So for this, again, it's just hardcore plugging in. So we're just going to throw the stuff in. So you're going to go 3 plus 2 cosine t and negative 1 plus 3 sine t. I'm going to freeze this because you're going to have to be real good at trig this unit. Okay, so try to get it as fast as you can. They're not horrible to solve, but and you're basically dealing with 0 or 1 or half. Do you think I can make it all day? What do you think? It's part of one. All right. So cosine of 0 is 1, so you just take 3 plus 2. Pi over 2 is 0, so it's 3. Pi is negative 1, right? And then 0, and then positive 1. Okay. All right, so now if you graph it, are you guys excited like I am? You ready? You're going to graph. You're going to go 5, negative 1. And then you're going to go 3, 2, and then 1, negative 1, 3, negative 4, and then 5, negative 1 again. Yeah, not just a circle. Hey! So this one just keeps flying around in there, right? Notice there's not like a bound on the T, like we just did a circle. Well, it just keeps going around and around, okay? So this is the fun part. You ready? You guys, this is so exciting. Is now we're going to come up with the Cartesian equation or the rectangular equation. I wish people would just agree in math. It's really frustrating, honestly, what the names of stuff is. So it's got to be a name for everything. Okay, so this is usually like not horrible because like algebra stuff, you know, like I usually like solve for t, you know. But like if I solve for t on these, they're like inverses and like annoying things. So I'm going to use strategy. You ready? I'm going to use a Cartesian equation that has sines and cosines in it. Okay. So, for example, okay, you ready? Do you know an equation with sine and cosine in it off the top of your head?
Cosine plus sine equals 1.
Look at that guy. Your little Pythagorean identity. You remember? This guy. Remember? That's like my MVP cosine sine equation. Right? So you're like, Mr. Arden, there's like T's in there. What are you doing? Well, watch what I'm going to do. I know this seems kind of goofy. Okay. Not much has happened. I just moved this square just so everyone gets less anxiety about it. Okay. And this is the plan. I can put all my x junk in for the cosine, right? Kind of. Think about it, because here's cosine, right? So I can do some algebra finagling to get x junk in for my cosine, okay? And then I can do some algebra finagling to put y stuff into my sine thing, right? So like, here's the plan. I'm gonna take this guy and just algebraically goof around with it. I'm gonna rewrite it, so, oh my gosh, what's happening? Plus 2 cosine t. I can solve, like, see, this is cute. I get x minus 3 all over 2. Leave it like this, because this is the grand finale. Just wait. So now I've got some x junk to throw in for cosine, right? Which is like rectangular Cartesian, whatever they're feeling to call it that day. Okay? And then this guy, if I finagle around with that one, you get y plus 1 equals 3 sine t. And you get y plus 1 all over 3 equals sine t. And I can throw this whole junk in there. Okay, so when I do that, this is technically Cartesian because it's got x's and y's. I eliminated them. Do you guys freak out right now or what? Because just like look at it. Let's keep going. 4. What? So is that like an ellipse? What? Do you remember? Oh, wait. Where's the center? Where's the center of the ellipse? Oh my gosh. Oh. And wait a second. Wait a sec. This 4? Oh my gosh, is that 2 and 2 away horizontally? What? And then 9? That's 3 and 3? What? So that's where ellipse formula came from. You just weren't smart enough then. Now you are.
No, I remember doing it.
Is that exciting? Stop it. You didn't remember. Okay, so here you go.